In this video I will show you how an early push-button telephone works. These telephones can only be used in combination with certain private telephone exchanges. I have built a converter to make them suitable for public exchanges such as the widespread step-by-step systems. Here you see an early matrix keypad that I've connected to my Strowger exchange. Let me show you how this works. I call the number 436. This video is rather long with lots of detail later on. If you're only interested in the full demo, you can skip to about the 5-minute mark. Some of you will remember telephones with a rotary dial for calling a number. You select a digit and you turn the dial clockwise towards the finger stop. The telephone sends an equivalent number of pulses to the exchange when the dial returns. A number of selectors is activated at the local exchange and often also in subsequent exchanges depending on the distance to the called telephone. These telephones with a rotary dial are still in use today, but they will be phased out with the transition of analog telephone networks to VoIP, which stands for Voice over Internet Protocol. Already in the 1950s, attempts were made to replace the rotary dial with a keypad. This was before the advent of cheap electronic components in the 1970s. Then it became possible to introduce DTMF, which stands for Dual-Tone Multi-Frequency Technology. DTMF sends two different tones for each number pressed on a keypad, allowing devices to send commands and data over telephone lines. The two tones are transmitted simultaneously for about 40 milliseconds. This is the DTMF table, where 16 characters are represented by a combination of two frequencies. The telephone network is typically restricted to 12 characters and the tones for A, B, C and D are not used. Here you hear a sequence of 16 characters in DTMF. The push-button telephones of the 1950s and 60s used a keypad that was designed to fit in the same space as the rotary dial of standard telephones. This is a Dutch HEMAF model of 1955 with a Philips keypad. The early ones had the keys in a circle, such as shown here. Some modern DTMF replicas also have push buttons in a circle. Later versions came with a matrix or grid distribution of the keys. These telephones can only be used in combination with a suitable telephone exchange or PABX, as they are called in the UK. The signaling makes use of the earth wire in the local telephone network. By switching the polarity between the A and B wires of the line and the earth wire, the exchange can work out which key is being pressed. The keypad circuit is passive and uses only diodes and resistors. In the Netherlands, these telephones were known as GDK, that stands for Gelijkstroom druktoetskiezer, which translates as direct current push-button dialer. In the UK, the technique is known as DC code signaling. These telephones were primarily intended for internal calls in private companies, but most of these private exchanges would also have the option to make an external call, typically with the intervention of an operator. In the 1950s, Shell managers in the Netherlands wanted local exchanges in their offices that could work with push-button telephones. They had seen how these telephones were used in the United States. Selecting a number is much quicker with a keypad than with a rotary dial, provided the exchange can deal with it. In the Netherlands, it was Philips telecommunications industry, known as PTI, that made their UB49A exchange suitable for GDK telephones. In the late 1960s, Philips also developed a GDK system that did not need an earth wire. This was intended for use with the public two-wire telephone network. The Dutch PTT, however, decided that modification of the exchanges would be too expensive. DTMF was around the corner and that may have played a role in the decision. Another reason was probably unreliability, because of the large variability in loop resistance in the telephone network. I got hold of 2 push-button telephones and a keypad, all based on the DC signaling technology. I will first demonstrate the operation before explaining how it works. Here we have the converter box that translates the keystrokes into pulses for my Strowger telephone exchange. At the top of that box is an early generation Philips keypad, which I refer to as GDK1. On the left is a second generation Philips telephone, referred to as GDK2. And at the bottom is a British model with type number SA4252. Let's first test the GDK1. I activate the keypad with the key start button. You hear the exchange getting ready. I call the number 436. Once the converter receives 3 digits, it starts sequencing the pulses for the exchange. Let me show you the movement of the selectors in my Strowger system. On completion of the dialing, the called phone starts ringing. The GDK1 has no telephone circuit, so the ringing cannot be stopped by putting a handset down. Therefore, the converter is programmed to stop the call after 5 seconds. In the same way, we can make a call using the second generation phone, the GDK2. You hear the dial tone when I lift the receiver. Now we call the number 333. The call finishes when I put the handset down. Turning the phone selector switch on the converter box connects the SA4252. Let's try 436 again. It's also possible to call one of these phones from another telephone. For example, let us call the SA4252. The number of the converter box is 371 in my case. The default setting of the converter is to have the phone connected to the exchange in order to allow incoming calls. For making a call, it's required to press the start button that activates the converter. Let's now have a closer look at the schematics if you're interested. This is a diagram of the first generation Philips push-button telephone, which I refer to as a GDK1. I don't have a complete telephone, it's just the keypad module that I'm going to use. I connected the A wire of the telephone circuit to the earth wire. I'll explain later why I did that. The 10K and 22K resistors are added externally to create different voltage levels at the earth wire for each keystroke. The numbers and symbols next to the switches indicate which switch closes when the respective key is pressed. Notice that more than one switch may close. For example, 3 switches close when the number 8 key is pressed. Here you see in red where current flows when I connect the A wire to the plus 5 volt and the B wire to ground. It is shown that the switch V opens to disconnect the telephone circuit if it's present. This table shows that the voltage at the E wire is 940 mV when the number 8 key is pressed. This is the measured voltage. It can also be calculated taking into account a 600 mV drop across the diode. Now we reverse the polarity. The B wire is at 5 volt and the A wire is at ground. 2 other switches pass current from B to A. The voltage at the earth wire E is 2.43 volt. This table shows that for each keystroke there is a different combination of voltages when the polarity is alternating. None of the keys has the same combination as any other key. Also, there is a distinct 5 volt at the E-wire if no key is pressed. That is required to detect a key release, as I will explain later. The exchanges that can deal with DC signaling use relays to switch polarity between the A wire and earth and the B wire and earth, respectively. Here is a simplified schematic of the register in the Philips UB49A exchange that interprets the keystrokes of a GDK telephone. I have not tried to mimic the operation of this register. My approach is different with the same result. I use an Arduino microcontroller to switch the polarity of the A and B wires and measure the voltage at the E wire. Each voltage translates into a number of counts in the Arduino program. The combination of counts then determines which key has been pressed. The principle as explained for the GDK1 is the same for the two other telephones that were shown earlier. For the SA4252, I've made a small modification to create a table of sufficiently different voltages at the E-wire. I added 3 resistors externally to the keypad as shown here. The keypads of the early Philips push-button telephones had a complex arrangement of switches. In my matrix version of the GDK1 keypad, the switching is done with reed relays. The levers connected to the keys hold miniature magnets. These levers with magnets activate the reed relays for some keys more than once simultaneously. Some of the switches were not working when I got the keypad module. To try and repair the unit, I opened it, ignoring that the holding screws were sealed with paint. That ignorance was punished. The entire contraption fell apart with more than 20 tiny springs and a full set of levers spread across the table. Wow! But I found the cause of the failing switches though. 2 tiny magnets had fallen out of a lever. That was easy to fix. But then, how to put the set together without any instructions? As an engineer, I love challenges, but this was a tough one. After puzzling for a couple of hours, I managed to fix it. All switches worked again. This photo shows the 2 telephones and the converter box with the GDK1 keypad at the top. At the bottom right are the keypad start button and the reset button for the Arduino. It should normally not be necessary to use the reset button, but I just added this because the button on the Arduino board is not accessible. Here is a view of the wiring inside the converter box. On the left are the phone selector switch and the RJ12 connectors for the telephones. Next to that are 6 songle relays. The Arduino itself is hidden underneath the black screw shield. At the bottom right is a 7805 voltage regulator that provides power to the relays independently of the Arduino. The supply of the box itself is by a 9-volt adapter. This figure represents the circuit diagram of the converter. At the top left is the simplified schematic of the SA4252 telephone. The original keypad circuit did not have resistors. That did not give sufficient distinction between the various voltages at the earth wire to reliably determine which key is pushed. I therefore decided to slightly modify the circuit and add 3 resistors, as shown in red. You will now notice the similarity with the GDK1 circuit in the middle on the left. The main difference is the combination of contacts for each key. The circuit of the GDK2 is different, where it has no connected earth wire and it uses another set of resistors. The phone selector switch has 3 positions for choosing which telephone or keypad is connected to the converter. The Arduino is informed about that choice by monitoring analog input A2. The input is 0 volt when the SA4252 is selected, 2.5 volt for GDK1 and 5 volt for GDK2. Analog input A1 is connected to the earth wire of either SA4252 or GDK1. The operation is slightly different for GDK2 because there is no earth wire. Here the test loop has a 500 ohm resistor in series. That allows input A0 to measure the voltage drop from 5 volt for various switch combinations. The choice of 500 ohm is more or less dictated by the voltage drop in the telephone circuit when no key is pushed and the handset is lifted. The resistance in a telephone circuit is not well defined, therefore the voltage at A0 may vary considerably. between 1.5 and 3.5 volt. However, the 2K7 and 7K5 resistors allow sufficient margin for the voltages to stay between 0 and 1 volt and 4 and 5 volt respectively, when any key is pushed. The Arduino controls 6 5-volt dongle relays. Relay L switches a telephone either to the A wire of the exchange line or to the converter. The default connection is with the exchange to allow calls to come in when the converter is idle. Relay S protects input A1 from the high voltage on the line when the bell is activated. Let's assume that SA4252 wants to call the number 436. The exchange responds with dial tone when the handset is lifted. A loop is now created via the normally closed contact of relay L and the telephone circuit. The converter is activated by pressing the keypad Start button. Relay L and Relay S switch simultaneously. The telephone is now connected to the converter. The exchange is held by switching a 500 ohm bell coil between the A and B wire of the line, using Relay H. The converter is ready to accept digits from the keypad. The non-numeric keys are not used. The voltage at the E wire is read at input A1. The voltage is defined by the 10K and 22K resistors when no key is pressed. It's approximately 3.45 volt. A loop is formed between the E wire and the B wire of the keypad circuit when the number 4 key is pressed. You will notice that switch MS1 opens to isolate the telephone circuit while switch CDSI connects the E wire. The various resistors create a voltage of approximately 420 mV at Arduino input A1. After 10 milliseconds, the polarity of the A and B wires of the keypad is reversed by operating relays P1 and P2. 30 milliseconds later, the voltage is read again. Now the voltage at A1 reads 4.6 volt. The combination of both voltages determines which key has been pressed. A margin of plus and minus 20 counts, which equates to 100 mV, allows for small supply voltage fluctuations. Arduino waits for the key to be released. A voltage of approximately 3.45 volt confirms that. There is no need for switching to polarity to detect key release. My Strowger exchange operates with 3-digit numbers. After 3 keys have been selected, the converter starts sequencing the dial pulses to the exchange. Relay D operates the interrupt contact between the A and B wire. The contact opens for 67 milliseconds and closes for 33 milliseconds. The exchange is handed back to the telephone circuit at the end of the sequence. Relays H, L and S release. The call ends when the handset is returned to the cradle. The phone is now ready to receive calls. My GDK1 has no telephone circuit. The number selection is identical to the SA4252, but the end of the dial process is different. Now the line cannot be handed back to the telephone circuit. The exchange is therefore held by relay H for 5 seconds. GDK2 has no earth wire. The detection of key movement is somewhat different from the other two. Here the circuit is powered from the Arduino 5V source with a 500 ohm resistor in series. The voltage drop across that resistor is proportional to the current in the keypad circuit. The polarity is switched behind that resistor, so the voltage at A0 is always positive. The voltage is 4.3 volt when the number 4 key is pressed and the A wire is positive. It is 5 volt when the B wire is positive, because the diode blocks the reverse current. This concludes my explanation of the operation. For those that are interested, you can find the Arduino code on GitHub. Here is the reference. It may be concluded that it's possible to use DC code signaling telephones in combination with pulse-driven number selectors such as Strowger. They were, however, never applied in a public telephone system that relied on two-wire network. One of the reasons is the inaccuracy of the loop resistance. That comes into play when the converter is located at the exchange. It may cause erroneous digit selection. The alternative would have been to house the converter inside the subscriber's apparatus. The required electronic components were either not yet available or they were too expensive. A new concept of push-button telephones emerged in the 1970s based on dual-tone multi-frequency or DTMF technology. DC code signaling was still used in private systems, but it was gradually phased out. This concludes my story. I would like to thank John Mulrain of the Telecommunications Heritage Group and Arnold Abels and Bob Groenewoud of the Howling Telephone Museum in Rotterdam for their help with this project. I hope you learned something today. Thanks for watching. Till next time.